Welcome to Data Science Tutorial. My name is Richard Kirschner with the Simplilearn team. That is www.simplilearn.com. Get certified, get ahead. What's in it for you today? We're going to cover what is data science, need for data science life cycle, data science components, data science applications, and a hands-on demo in Python. So what is data science? Data science is the field of study that deals with modern scientific techniques, statistical methods, and algorithms to derive insights from vast volumes of data. Companies using data science are very numerous. With companies generating data every minute, there is a need to make sense of this data. Mu Sigma, Fractal, Fidelity, Intel, Genpact, Qubela, Amazon, Trendince, Connect the dots. Just about every business out there nowadays uses some form of data science, even if it's indirectly, to help govern their business and help them grow and compete in the business world. And we use the data science to find unseen patterns within the data, analyze and draw insights from our data, and solve business problems and make decisions. And the data science has a life cycle. We start with our data discovery. Then we go through data preparation, exploratory data analysis, data modeling, interpret the results, and back to data discovery. When we talk about data discovery involves asking the right questions, identifying the business problems, finding the best solution, and gathering correct data from relevant sources for analysis. This is, in the data science life cycle, the most important step. Now, in general, it only involves like a small percentage of the time you spend on this. But if you're not asking the right questions, you can't go in the right direction. Data preparation. Data preparation deals with cleaning the data, finding the inconsistencies, tackling missing values, converting it into the right format, and making it ready for analysis. When I'm running the data science life cycle, this is probably where the most time is spent. Data can be so messy. You have to break it down into different parts. You have to import the different pieces from different databases. Are you dealing with straight numbers off of spreadsheets and cells, or are you dealing with text documents and natural language tokenization? Exploratory data analysis. Analyze and visualize the data using different charts and graphs to find significant patterns and hidden trends. That helps to understand the data better. The building of the charts is very creative. Probably one of the more enjoyable parts is be able to come in there and describe the data and show that to the shareholders. Then we dive into data modeling. Use classification, regression, and clustering algorithms to build machine learning models that can help predict and forecast future trends. This is where we start getting into predictions. What's next? Where's it going to go? And then interpret the results. Validate the model results, draw the final conclusion, and check if the performance of the model is in line with the requirements. The final step is the one that you set up in front of the board members and give them suggestions as to what's next. Where are we going to spend our marketing money? Where are we going to start preparing our firefighters for the next fire breaks next year? What is the weather patterns coming in? This is where you interpret the results and say how accurate they are. Are they valid? Is it something we're going to keep, or are we going to throw it out and have to start over? When we look at data science components, there's the mathematics, statistics, domain expertise, data engineering, data visualization, and machine learning. When we sum this up in data science, really this point in all of this you want to focus on first is domain expertise. Now, when you're taking your classes, obviously you want to go through the mathematics, the statistics, the data engineering, the data visualization, the machine learning, and learning all those tools. But it really, in the job field, the domain expertise comes in. Because if you're really good with business and you go into business with these tools, then you're able to ask the right questions and deal with it. When we talk about the tools in data science and where they sit, there is a data analysis. Data analysis focuses more on statistics and mathematics, where the data science side where the data science side focuses more on the machine learning, data visualization. And then there's database management, which really focuses on the data engineering part of it and how to manage that data and the data flow. And you can see all these components come together, and then they form the data science. And we talk about tools in data science. We have SAS, we have MATLAB, we have SQL, you have your Apache Spark, your R, Tableau, Python. Right now in the programming languages, Python is probably the most widely used, with R coming in a close second. The reason for that is these are both open source and anybody can use them. When we look at SAS and Tableau, those are two packages that are paid for, which have a lot of automation behind them. So a lot of larger companies will pay for those packages because they help work out a lot of the back-end stuff before you even need to use them. And of course we have Apache Spark. You almost have to know Apache Spark and the growing data lakes today. That's your big data. How do you distribute this if you're going to process it over a large amount of data? When we look at data science applications, there's internet search, very common. You enter your Google thing and it uses the data science algorithms to figure out what to return. Voice assistants, analyzing the voice coming in and connecting it with whatever patterns they need to activate so you can ask it to turn your lights on in the living room. Healthcare, biggest field growing right now. How do we analyze health data from a smartwatch and figure out how to know when a disease is being spread across the world? Healthcare, how do we identify cancer versus non-cancer so we know who to prioritize and get them in for surgery where other people might not need that immediate care? And even identifying problems somebody might have with their health long before they even happen. What a neat thing to do instead of waiting until you have a heart attack to know months ahead of time that you're having heart conditions. Logistics, how do we get from point A to point B? If you ever look at some of the major distributors, they pre-ship things based on what they guess people are going to need. This way you get your stuff right in the mailbox the day after you order it. E-commerce, huge in there because you have to know what kind of marketing we're going to put out. Who are we selling to? What's our target audience? Robotics, one of the funner ones when you're coming up into the future is how do we automate the different tasks we have, from self-driving cars to manufacturing lines to maybe even a self-robotic chef in the kitchen. So when we talk about solving problems with data science, we have to ask possible questions and the desired algorithms. And these really are kind of an overview of some of the terminology you'll want to know in data science. So when we talk about that, how much or how many? We're talking about regression. Regression basically means a number. If you've ever seen stock charts, you see the guess at what the next sales price is or buy price is. That's all on your regression side. Is it A or B? Classification. Is that a dog or a cat that my photo took a picture of? How is this organized? Clustering. This is where we take things that look alike and put them together so that we can then make predictions on it. How different is this? Just like you have clustering, you have the opposite, anomaly detection. How do we find things that don't fit in? Where are the outliers? What are things we might need to look at that aren't in our model? And what to do next? Reinforced learning. This is probably the newest market, is how do we set something up where as the data comes in, it learns from the new data as to what the next action is going to take. Most of these are combined. So when we talk about regression, classification, clustering, anomaly detection, reinforced learning, a lot of times when you put your model together, you might have multiple parts of this. We might look at the clustering of data and then feed it into a classification. Is this a bad loan to make at the bank, or is this a good loan to give? And from there we might start looking at, when we start clustering these things as good and bad and what kind of setup is, we then might run it through a regression model to say, hey, what is the dollar amount this person should be allowed to take a loan out? And you can see that all of these start coming in, and then a lot of the models, reinforced learning, we talk about like bank loans and things like that, once a year they have to rerun those algorithms. And so that's like a human run reinforced learning. Now we're starting to automate that so that as the data comes in real time, the models start updating themselves. They start figuring out a way to solve new problems as they occur. And of course in robotics, reinforcement learning is one of the biggest growing fields. Algorithms used in data science: linear regression, logistic regression. When you're looking at both of these, think numbers. We're talking regression models. And so linear regression figures out the best line through the data. Maybe it's looking for a curved line. Logistic regression starts looking at data on a continuum so that it goes to an exponential. You have a spot where it might be one or the other, and then you know what it is as it goes to one side or the other. Decision tree, wonderful tool. If you they used to call it a hack, now it's becoming mainstream, to look at the back end, what made the decision. So it's really easy to trace back to how you arrived at the decision. Decision trees are kind of nice that way. Nearest neighbors. K-nearest neighbors is your clustering. K-means clustering. Hierarchical clustering. So hierarchical starts dividing them and builds a hierarchy where the K-means and the K-nearest neighbor look for things that kind of connect each other. How close are they in data format? DB scan, another form of clustering your data. Principal component analysis. So we start breaking up and looking at the different components in our data coming in. These are all algorithms used in data science, and there are more. These are kind of the mainline ones. And each one of these has many settings which you can play with to build a better model to predict your data and where you want it to go. Let's go ahead and take a hands-on demo and just see, what does this look like? Now I'm going to go ahead and use the Anaconda Navigator and the which is your Jupyter Notebook, which will then open up in Google Chrome. This is one of the IDEs, or ways of editing Python code. I like this one because it, one, protects my computer and creates its own kind of container, and two, it's got a really nice visual demo for doing Python. Certainly you can use a number of other different tools like PyCharm. Is another real popular one. You can actually access PyCharm code through the Anaconda Navigator now. And there's a lot of other tools on there that each have their benefit. And we come into our Jupyter Notebook. I go ahead and create a new Python. I've already done that. And we'll start with a logistics regression model, just so you can see what this looks like in code. We'll actually do two of these as we go through this, and take a look and see what that code looks like in Python. Now, the first thing we want to go ahead and do is load up all our parts modules that we need in our Python code. I'll go ahead and run that, and you'll see here I'm going to ignore warnings, because some of the stuff we're doing, we're just looking at it, and as you go from one version of Python to one version of whatever the scikit, or in this case the SC package, you'll see some warnings come up. They're not really important right now. And then we're going to go ahead and use the German credit data CSV. And so when I run this, this is all loaded up. Now let's go ahead and just open up this CSV file so you can see what that looks like. And here it is. Here's our German credit data file. We'll go ahead and just open that up with, let's do WordPad is fine because it's a Word document. And when we open that up, you can see right here it's just a bunch of comma separated values. We have across the top, it actually has columns on here, so our first row is a bunch of columns. And then of course we look down here. Oops, I just moved stuff around, but that's okay, I'm not going to save it. And you can see the values, AL1, AL4, whatever that means, or A14 I guess, and then some sorted numbers on here. And we'll take a closer look when we get into the program and looking at the data. For right now we've loaded that under credit DF. And at this point, I want to just kind of take a detour back to the life cycle of data science so we can see how that fits in there. And so we've already done our data discovery. We have a little data prep, but the data is pretty clean. It already comes in preset on there. We might do a little data preparation in here. We're going to start looking at exploring the data analysis and building a data model and then interpreting the results. So really we're focusing on the last three steps of this. The data discovery would be start asking questions of what do we want in there? Is this going to be a good loan, a bad loan? What do we want to get out of this data? Where are we going with it? That would be part of the data discovery. And a lot of times that might be a meeting you have with the management in the office or whatever. And then data preparation is, of course, cleaning the data up, making sure you know where the source came from, all those kind of fun things that go into making sure you have good data coming in. Now you'll notice here we're using pandas. Whoops, I drew it through the pandas. And we're going to go ahead and read it as a pandas data frame. And of course pandas sits on NumPy, so a lot of stuff you do with pandas can go right into NumPy very easily. And the reason I bring this up is because pandas has a lot of tools in there for just looking at the data real quick and easy. And so the first one we want to go ahead and do is do credit.df or credit_df, our data we read in, info, and just see what that looks like. And when we go ahead and print this out, you can see here we have 13 columns. Remember we were looking at our data and it had that row you couldn't read across the top. Then it has non-null count, how many values don't have null, what kind of objects are they, they're an object, an integer, different things like that. And we look at object, is it a checking account? This is probably text on here. Duration, how long, credit history, amount, savings account, present employed since. So a lot of different numbers coming in here, and these are just the columns we're looking at. And if you're going to look at the columns, it's kind of nice to actually look at the data. And so we'll use the pandas to go ahead and print it out just like you would on a spreadsheet. Hard to see them all on here, but you can see we have, here's our row across the top because Panda does such a good job sorting out columns and the actual data. Checking account A11, A12, A14. Not sure what that means. Duration, how long they've had it. Credit history. Not sure what the A33 or A34 means. I'm sure it has a special meaning on there. The amount. Here's our savings account and all the information on that. And this is actually a much more easy to read view than what we had before. As far as like that text file, when you're just looking at data through the database, sometimes those can be really hard to read. This you can really see, and if I take it down a notch, I can get all the columns in here. We'll go ahead and keep it zoomed in just so we can see that what's going on a little easier. And then we can also do creditdf.ilocation. The ilocation feature in the pandas is going to go ahead and do rows 0 through 5, and we're going to look at columns 1 through 7. And let's go ahead and just run that. And you can see right here how we just split it up. So it's real easy to manipulate our data and get a smaller view of different parts of the data as we're going through it. And just like we can look at the first 7 columns, we can also look at the last 7 columns. Same kind of format. We're looking at rows 0 through 5, column 7 to the end, if you leave the number out there. And you can see we can easily now look at this on a smaller screen, much better for displaying. Those are just tricks to help you display your information so that when you present this in front of a group of people, it makes it very easy to read, or you can just copy this out and put it into a document, that kind of thing. And then we also like to go ahead and do like credit status value counts and things like that. Again, we're just looking at the different sets of information on here. And in our pandas data frame, value counts is we're looking at unique values. So there's a lot of unique values in here. That's 700 and 300. That's a significantly diverse set of data. And if we look at the data, one of the things we're looking at is the status 01, 001. And I'm going to guess that that means that it is either default or not default. So that's probably what we're going to want to look for. Hopefully you've had your specialty in domain. Remember we talked about the different parts of data science. Domain is what field it is in. This would be in banks and loans. And so if we want to figure out what the status of a new loan is, we're going to separate the status out. And so if we take our X features equals a list of the columns, that's all this is, credit_df.columns. We remove status, and then we go ahead and this will print our features out, and you can see it's everything but the status on the end. Because that's what we want to predict. We want to predict the new data, whether that status is 0 or 1 or not. And next we want to do a little bit more data preparation. We're going to go ahead and encode. And we're going to take an encode credit DF. We're going to create that off of our setup on here. And you're going to ask, well, what are we encoding on here? Well, when we go up to here, let me just go back all the way. When we're looking at all this information up here, you can see there's object, object, object. Well, if I'm doing a prediction and something's just a random object, it doesn't really mean anything. There's no numbers to process. And so when we come down a little further, we can see down here that we are looking at A65. I'm not sure what A65 means. We're looking at A93, personal status. We're looking at A143. These aren't actual numbers. There's some kind of code that the bank put in, probably. And so for our model, they really don't mean anything unless we convert them to numbers. And you convert them to numbers by literally creating a bunch of yes/nos. So instead of thinking it as A173 and A172 as being 0, 1, and if you had A174 maybe 0, 1, 2, you would think of this as a label, A173 is true or false. And then you'd have another label, A172 is true or false. So for every unique job in here, that it becomes another feature added in, and it's on or off, it's true or false. That's what this encoding is doing. And we'll go ahead and list our encoding as it comes out. And if you come up here, you can see it did exactly what I was describing. We've now encoded it. So here's checking account A13, checking account A12, 14, A31. Here's all of our checking account numbers. So there was 3 of them. Here's our credit history, A31, A32, A33, A34. Again, the computer has no idea of knowing what those are. All it knows is those are each unique features. And the same thing with the savings account, A62, and so on, going down. And so once we have our nice list of there, we can go ahead and do, let me pull this in. Here we go. Let's look at our new data set. And if we go ahead and run the new data set, we have our encode credit DF checking, and we're just going to look at these and look at the head. This is just the first few of these, so we can see what it actually looks like in the data. And just like I said, it's now 0, 0, 0, 0, 1, 1, 0, 0. This first column is just the count, 0, 1, 2, 3, 4. That's not part of the data. But you can see here that it just puts a check mark of 1 because it's an AC A12, and we have a checking account AC A14 where it's also a check mark of 1 going across. So we've done a little data preparation. We've come in here and done some exploratory data analysis. And now we want to start building our data model. And we'll kind of go back and forth between exploratory data analysis and data model, and then interpreting the results on this. And so when we go ahead and import our stats models as API as SM, now a lot of times we use the sklearn or the scikit models. In this one we're going to go ahead and use the SM model from stats models, which is pretty common for doing a very basic logistics regression model. And then from the scikit we're going to have our train test split. With any data, you want to go ahead and train your model, and then you need something to test it on, some unknown data, so you can see how well you did. Very common in your setting up your models is to split it up into your training set and your testing set. And what I want you to notice on here is we have xtrain. Well, what is xtrain? That's all the columns except for the last one, which was the status. Was it default or was it in good standing? And then, of course, our x-test is part of the data. We're going to split that up by 0.3, so 30% of the data is going to be, 30% of our rows are going to be put in the x-test, and the y-train and y-test is just the status. And then we create our, once we've created our data and split it up, we go ahead and create our model, and it's a logit. We're just going to call it logit, but a lot of times you end up seeing logit model. With logit, it equals the sm.logit xtrain, ytrain xtrain. In sklearn it's always xtrain ytrain, but in the stats model, it's reversed on there. And then they go ahead and run the fit. So we load the data up and then we fit it. And then we can go ahead and summarize that model and see what it looks like. And let's go ahead and run that. It takes it just a moment. And we get a nice summary of our data. Again, we're still looking at the data. And we have, takes just a moment to kind of feed through, and you can certainly see where we have our coefficient, which has to do with the weights in the model. Standard error, that's very important as we look at this coefficient and how it affects the model. P is greater than the absolute value of z, 0.025. These are all your statistical notes on here. So as you look at these, you might look at like how big is a standard error. That's one of the big ones that I usually look at. As we go up and we start looking at the different things, the higher the error, the less, the more we want to be a little careful of it. The lower the error, the better. In more general terms, they also have dealing with the model and its iterations. You can see some general status on here. How many iterations did it have to go through before I was able to come up with the numbers? Because it kind of guesses. It's playing a high-low game, and it takes it 6 iterations till it finds what it considers the best fit. And you can see there's more information up here as far as when it converged, how it converged, and so on. Now, when we have our summary up there, one of the questions starts coming in. Remember I told you we're looking at like our standard error and how these numbers all are telling us how important each one of these features is in running our prediction. And if you have a ton of features and some of them are just kind of all over the place, all they do is create noise. So we really want to get rid of them. They also cause issues in that if you're running a huge amount of data and you have to rerun this model over and over again, this can really tax your time, and so you're losing both time, money, and your results might not be as good because they might be weighted based on some of these very fuzzy numbers. So we're going to look at significant variables and put together a little routine for that. Again, we've come in, if you remember from back here, we're still in kind of an exploratory data analysis and data modeling. They kind of go hand in hand sometimes. We haven't quite got to interpreting the results and running predictions. And so we'll go ahead and build this thing on here. It looks at the LM values, so that's coming up here where this was generated. I'd have to actually look that up for this particular model because I usually use the Simplilearn version of this. So as we look at this, we're going to look at the p-values of our variables, and basically we're looking to see how good the p-values are. If they're less than or equal to 0.05, we probably those are probably solid values, and if they're greater than that, then probably we're not interested in them. And so let's go ahead and run this, and we see that when we pull out all the values that are less than or equal to 0.05 for the p-values, and if we go up here, here we go, here's our p. I knew it was up here, I just wasn't seeing it correctly. So you can probably see duration, that's going to be good. Amount, 0.01, that looks good. Instant INST rate, which I'm guessing is the percentage rate or the interest. I was trying to say INST and interest at the same time. So we have our interest rate and all that. If we come down here, we see duration, amount, our instant rate, age, checking account A13, checking account A14, credit history A34, savings account A65. These are our primary features. These ones are related when we look at the data. These are the ones that are going to predict whether it's a good or bad loan. And so now that we know which ones work, we want to go ahead and recreate our SM model, or our final logit model. And you'll see here we now have the X train, the Y train, and then instead of the X train, it's X train significant variables right there. So all we're doing is running this just on the significant variables in the setup. And we'll go ahead and fit it. And you can see here you can actually double bracket and do it all in one line. Up above we had to do it in the 2 lines, which is how the setup is for this particular module. And then we'll go ahead and do a final legit summary and just see what that looks like. And we can see here's our p-scores. Remember, they're all supposed to be under underneath the 0.05. These are all under 0.05. You can see up here are different statuses as far as how it ran. It still took 6 iterations to go through the data. the date, and so forth. And now that we have a solid model, and that's, if you remember correctly, let me flip back on over here. We've done our data modeling. We've created a solid model, and so now we need to actually run a prediction so that we can interpret the results and weigh in on that and see how good they are. And so for that, I'm going to go ahead and, let's see, find it over here. Y predict. So we have our model that we created. We want to go ahead and create our Y predict, and it's based on our final eject. And here's the magic word predict, or dot predict. And so this is where we're going to come in and actually get our predictions on here. Then our model comes up. And remember, we're testing, X test is going in. There's our X test, and it's only the significant variables. So we've created our model. Now we want to push in our test version that's never seen this data before. So this is all new. And then we're just going to take a random sample to see what it looks like. What do those predictions look like? In this random sample, we're just looking at 10 of these. And you can see here is the actual number. It says 0.08, gives us a 1. 0.07. This is our probability number, which is, I would have to actually look to see whether higher or lower is better. I'm guessing the closer to 0, the better it is, but I'm not completely sure on that. I have to actually look up and see with this particular framework. But you can see the actual prediction, 1, 0, 0, 0. So I guess this is a good loan, a bunch of defaults, and some good loans. That's what it predicts it's going to come out as. Now, just looking at the data, it's confusing. You have different models, they have different setup, they have the predicted probability comes out on this, and other models it doesn't. So you really need a tool to dig deeper into the setup to understand what this means. And so what we're going to do is we're going to take our predicted values, which you can see right here has an actual predicted probability, and then we're going to go ahead and insert on there from a sample. Let me just run this because it'll make a lot more sense. We have our actual value and our predicted value. So this is what we predicted, and this is the actual setup. If we just look at this right off the bat, we can see that we predicted 0 and this was a 1. These all came out correct. Number 332 came out correct. 917 was an actual. They were good on their loan and they predicted it's going to be a default. You start to see that there's some variance. So how do we measure that? How do we know whether our model was any good or not? Well, for that we're going to go ahead and load up a nice graph, and we'll use, for our graph, we'll import matplotlib pyplot and Seaborn. Seaborn sits on matplotlib. And this matplotlib inline is just because I'm using Jupyter Notebook. With the new version I'm in, it doesn't even need it, but I tend to leave it in for older versions. And then we import from our sklearn metrics. This is your scikit. Scikit is the main package, and sklearn is how it looks on here. And we'll go ahead and run that so it's nicely loaded. And then we'll go ahead and create a little routine in just a moment here to print this out so we can see what that looks like. And this metrics is kind of a fun metrics because it tells you like how many you have correct on the correct one, how many you had wrong on the wrong one. And this top part is just all a draw routine. So it comes in here and has our actual and our predicted, and as our CM metrics, it breaks it up, puts it into the heat map. The SN heat map gives it some colors, add some labels, and then we go ahead and show it, and we're just going to dump that in there and run that. And you can spend forever building graphics. It's so much fun. We come in here, we have bad credit, good credit. We have bad credit, good credit. We have predicted label. And so when you look at this, you can see here it had, on the good credit, it tells you how well it predicted it and how many false positive it has. And on our bad credit, here we have bad credit, it said 30 of those were bad credit. It predicted them bad credit. While 21 were good credit that it predicted would be bad credit. And then we have here, we have 188 that were good credit. but the actual value, and then it had 61 that were bad credit that it said were predicted good credit. So at this point, you'd look at this and you'd say, well, if I'm predicting this is our good credit here. Let me flip this on over here. And this is our bad credit. There we go. So we have bad credit, good credit. You start looking at that and you say, okay, can we afford that many defaults after 5 years or whatever it is? And so those are the questions you start asking is, does this model work good enough to predict whether we should give these people loans or not? You're always going to have somebody default on them. And again, that starts going into domain. Banking domain, something I don't know very much about. Clearly I know whether I default on a loan or not, which I don't, and I try very hard not to. And then if we're going to draw the chart, which is really nice to have just a clear visual chart. Metrics also has our classification report, and you can see these are just the numbers we were looking at. They let us know the precision, our F-score and recall and all that stuff on here. You can just print a straight out metrics classification report. Now, we looked at a regression model. Let's go ahead and look at a clustering model to see what that looks like. And we'll go ahead and create a new Python on there. And this is going to be our clustering setup. Let me flip this off and switch on over to my clustering menu. In this case, we're going to be looking at k-means clustering. So let's just put that up here. K-means clustering. Now, the last one was a regression model. So it figured out coefficients for lines. You can go back to your old Euclidean geometry or the algebra expression for slope on a line, y equals mx plus b or whatever. And it goes on from there as far as finding distances and figuring out the lines on there. This is a little bit different. When we talk about clustering, it uses similar ideas, but it has to do with edges, 2 points, and how do you figure out a distance between 2 points and what does that mean? Now, you'll see here we have our pandas PD, our numpy is NP, our matplot library. Seaborn sits on matplot library as we talked about. They've added some parameters here as far as colors, and then we did an inline for the matplot library. Again, that's not really necessary, even in the new version of the Jupyter Notebook. In the old version of Jupyter Notebook, if you didn't do that, it would just kind of hang or disappear. And then we're going to import some data. It's important to have our data set up in here. And instead of looking at this and guessing what the data is, usually you open up the CSV file at this time. Let's just go ahead and print it under the df head. Because really those text files are so messy, and you look at the df head and it's easy to look at. Whoops, had a path issue there. So college data, it's a CSV, so it automatically knows there's a .csv on there. And we can see here that they downloaded from a number of colleges, Abilene Christian University, Adelphi University, Adrian College, and then it has whether it's private, I'm guessing yes or no, apps, I'm not sure what that is, acceptance rate, applications I'm betting, and then the acceptance rate, enrollment, top 10%, top 2, 5%, undergrad, so on. So these are just statistics based on the college, their college getting into a college. And just like we did before, let's explore the data. If you can remember from the chart we were looking at, we're going through our data discovery, data preparation, and exploratory data analysis. So we're really kind of looking at the data and what do we have here, what came in. At this point, the data has already been prepared. We are not doing a whole lot as far as getting rid of null values and finding out whether it's bad data or good data and that kind of thing. And data discovery would be figuring out which data to send. So that we've already done. So we're going to go with the exploratory data, jump into data modeling, and interpret the results just like we did with the other one. And we'll go ahead and use the Panda tool to get the info. DF, you'll see DF very commonly. It just stands for data frame. A lot of people use it as a generic setup when they import from Pandas. And so we have our info, and you can see right here, Non-null numbers, here's our count. So each one of these has 777 non-null values. And again, here's our type of data we're dealing with. And if you remember from last time, here's an object. This was our yes or no. Everything else looks like it's integer. We do have a float value here. Integer. Floats and integers, usually when you're running them on a prediction, they're pretty interchangeable in a lot of cases. But whether it's private, true or false, that's pretty important on here. The fact that they could probably be switched to a 0 or 1 is pretty helpful also. And if we're going to look at all that data, we can go ahead and describe it. So there's our data frame, describe. And you have the same thing. Here's our count. All these should be 777. We have the mean value, so you can actually look at what our average is, standard deviation, minimum, different quartiles, 25, 50, the third quartile, that's so on. And of course our max value on there, min and max. And as we explore the data, we can do a lot of fun things on here. We're going to use our Seaborn, and we're going to look at room and board versus graduation date. We're going to add, this is going to be a heat map, so we're going to add whether it's a private college or not, how it fits, the size, the aspect ratio, and all that. That's what this line is here. Seaborn, you can almost do your own class on Matplotlib in Seaborn because there's so many features in there. But when you look at the very basics, you can throw up some data and have a nice colorful map set up. And here we have our graduation rate compared to room and board costs, and in private or public. So you can see that the graduation rate compared to room and board. Interesting thought. How much did I spend on room and board? Am I going to graduate the more I spend on room and board? And you can see numbers go up there in graduation rate, and you can see that the graduation rate tends to go way up for your private schools, and the room and board also continues to grow in private schools, kind of thing. It's kind of just a fun heat map. And we can explore other things in our doing our heat maps. We can look at out-of-state, whether it's out-of-state, undergrad, private again is one of our setups on here. And you can see here that for undergrad, there certainly is a lot more public schools, and whether it's out-of-state, interestingly enough, the out-of-state number goes way up, how many people coming from out-of-state into the school for the private schools. Just kind of fun things. If you're trying to figure out where you're going to go, maybe you'd want to do this for picking a bachelor's degree or a master's degree or something, or certainly you could also plot this with fun locations and download information on tourism sites if you're traveling, that kind of thing. You do the same kind of thing with. And we'll go ahead and throw out another map on here. Let me go and run this. This is a slightly different setup on here with the out-of-state. And so we're running, let's see, pull this up. Bins 20. The bins is each, how many bins are you going to split it into? And this is kind of a fun one where you can see private versus public. We have how many out-of-state, and I'd have to look this up to see what they picked on here. Oh, there we go. Okay, so you can see we have another chart that has to do with the out-of-state and the number of students coming in, and private and public. So a lot of different setups on here as we dig into the different graphing. So at this point, we've just been kind of looking at the graphs on here. Let's go ahead and import our cluster, our k-means cluster. And you can see here we have, we're going to call it KM, I guess for k-means, or maybe it's k-means model. I always label mine with model. Equals k-means in clusters equals 2, random state equals 90. And so when we cluster it, we're only going to cluster into 2 groups. That's what this is meaning here, across the different settings on there. And then we're going to go ahead and fit, and we're going to drop private. So we're not going to be looking at whether it's a private or public school. And we're just going to go ahead and run the cluster on there. And then once we run the cluster on there, we can actually look at cluster centers. Let's go ahead and do that on this. when we talk about k-means, let me run this. Boom, there we go. So we have all these different columns, and each of those columns has a center, and we start looking how the data comes together on those centers. That's what all these numbers, this is the hidden stuff behind the clusters on here. And so we can now do, maybe we'll create a little converter here. If private equals yes, return 1, else return 0. We're going to run our cluster private and apply the converter. And then we'll go ahead and print that out. Let me just show you what that looks like so you can see what we're doing here. And then we go ahead and do df cluster. We'll create a new column on here, private, apply converter. And we can see here it creates private apps except. We've just added on to our data frame on here. And we did that so that we can run the confusion matrix. Make sure we import our confusion matrix. We're going to do a classification report confusion matrix, and we'll go ahead and run this on our clustering. And as you can see here, as our predictions, here's our confusion matrix up here, just like we had on the other setup where it has how many false, true, false, false, true, false, and false, false. As your accuracy and our setup on there. This is really, if you're looking at where you want to go, maybe you're looking at where you want to go in a, I think more of a tourism thing, but for colleges, this is a great way for looking for a bachelor's or a master's. Coming in here and you can start finding out which one you want to go to based on this accuracy, whether it's private or public, or how many graduations are on there. So we looked at a couple examples, went through some of the parts of the cycle, whether using a k-means or linear regression model. And certainly this cycle and these models, you start to see that there are some similarities. We're doing the same thing and each model has a better setup depending on what you're trying to accomplish on there. I hope that you were able to get an overview of some of the things that you look at in data science in our data science tutorial. Welcome to Simplilearn. Thank you for joining us today. For more information, please visit www.simplilearn.com. Get certified, get ahead.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.